It's recording. See? We'll see if it works. Okay, so we covered dot product geometrically and algebraically, so now we are going on to scalar and vector projections. So an important application of the dot product is involving projections. So you can think of a projection like a shadow. So if you have the vector A from point O to point A, and you're projecting it onto vector B, then this O to N is what we call the scalar projection of vector A onto vector B. Okay. So basically, it's the horizontal component of vector A. So if your theta is less than 90 degrees, then A and B are pointing, somewhat in the same direction. You have this acute angle, so ON is here. If your vector A and B form an obtuse angle, the projection of A onto B is not on vector B. Okay, it's this scalar quantity over here. And in the case that the angle theta is 90 degrees, then what does the scalar projection equal? 0. Exactly. So in this case, ON is equal to 0. Here, ON will be negative, and here, ON would be positive. So to calculate the scalar projection of A onto B, what you want to do is isolate for A cos theta in the dot product formula, because that would be what we need for the scalar projection. Okay. So if you want to isolate for A cos B, then what do we have to divide both sides here by? Oh, horizontal component of A. Sorry. Both A and B? Remember, we want to isolate for A cos theta. So just magnitude of B. Yeah. Okay. So S projection A onto little b, like so. That's how we write it. So scalar projection of A onto B is equal to the dot product of A and B divided by the magnitude of B.
What's the point of using this method?
If I give you, well, I mean, we can use this for geometric vectors. We can use it for algebraic vectors. So either way. Okay. Any questions? Okay, a few things to keep in mind. ON is a scalar quantity, not a vector. And the scalar projection of A onto B in general is not equal to the scalar projection of B onto A. Okay? So if you look here, this is the projection of A onto B right here, this quantity, ON. Whereas if you flip it around so that we have the projection of B onto A, it'll be this quantity here. So for this one, scalar projection A onto B is dot product of A, B divided by magnitude of B. But here on this side, if you have scalar projection of B onto A, that would be the dot product of B and A, which is the same as the dot product of A and B, but then you're dividing this by what magnitude? By the magnitude of A, exactly. Okay? So even though the dot product A and B is equal to the dot product of B and A, the magnitude of A is not necessarily equal to B unless stated as such. So therefore, scalar projection of A onto B does not equal scalar projection of B onto A. Questions? Okay, and then the last point that you need to keep in mind, the scalar projection of A onto B is independent of the length of B. So in this case, if this vector B is this length, the projection of A onto B is this ON length. In this example, you can see that vector B is twice as long as in the previous example, but the scalar projection ON is still this same length. So ON, this is ON. So scalar projection of A onto B is the same even though magnitude of B is different. Any questions?